Howdy folks, it's me, Mr. Hess, back again here, and in this video I'm going to show you how to solve all the problems on the Chapter 7 review worksheet. Alright, so if you have your worksheet handy there on problem number 1, they give you a proportion that looks like this. Okay, on any proportion, you have a ratio set equal to another ratio, or fraction equals fraction, you might say. And the first thing you do to solve anything like this is cross multiply. So you're going to take the 3 times the 2x. So 3 times 2 is 6. So 3 times 2x would be 6x. And take this 2 times everything up here. That's the other cross multiplying we're going to do. So 2 times the quantity 4x plus 1. You got to distribute the 2. So 2 times 4x would be 8x. 2 times the 1 would be 2. That leaves us with what I call a sheriff bandit situation. Now normally I would get rid of the weaker one here, but if I do this just to show you here, that's going to leave you with nothing over here, 0. Over here you'd have 2x plus 2, and that's fine. I mean, now here you could just subtract this 2 over here. So now you have 2x equals negative 2, and then divide by this 2. As you can see, this gives you a negative value for x, but that's okay. You're allowed to have a negative value for x in a proportion. That's fine. Alright, so that was problem number 1. Problem number 2, a pitcher allowed 20 earned runs in 30 innings. At this rate, how many runs would the pitcher allow in 9 innings? Okay, so they're establishing a ratio there. They said a pitcher allows 20 earned runs in 30 innings pitched. Okay, so this is the innings down here. So at this rate, how many runs would the pitcher allow in 9 innings? So on the other half of our proportion, since I put innings on bottom here, I'm going to do the same here. And we want to know how many earned runs he would allow. Okay, so there's a good setup for our proportion. And just like we did on number 1, we begin by cross multiplying. So 30 times x is 30x. And 9 times 20 is 180. Divide by the 30, and then you'll have your x. In this case, that should come out to 6. So the pitcher will allow 6 earned runs over a 9-inning game. Okay. Erase this so I can keep going here. On problem number 3. Says the legs of a right triangle are 8.2 inches and 10 inches long. So we've got a right triangle. One of the legs is 8.2 inches and the other 10. And then it says the shorter leg of a second right triangle similar to the first is 15.4 inches long. Okay, so it's going to be similar to this one, and it's going to be the shorter leg. So you see how 8.2 is the shorter of these two? So on the new triangle that we're going to make over here that's similar to this first one, I'm going to put the shorter leg on the bottom over here as well, just so there's no confusion here. And they said that shorter leg is 15.4 inches long. And they want to know then, how long would that longer leg be, okay, of the second triangle? Okay, so if these two are in fact similar, like they said, then that means we should be able to set up a proportion to help us find this. Okay, and as long as you're consistent, you can't go wrong here. You know, if you see this as just a translation over where this corresponds with this side and that one with that one, you could say 10 over x equals 8.2 over 15.4. Or any equivalent proportion. You know, if you want to go 10 over 8.2 and then x over 15.4. You know, just be consistent in your pattern. Okay, and then of course, like we were doing earlier, we're going to cross multiply. So you'd have 8.2 times x equals 10 times 15.4, which is 154. Divide by the 8.2 and you got your x. If you divide that out, 154 divided by 8.2. You'll have to round this. It's a big long decimal. It's approximately 18.78. Okay, that was problem number 3. Forgot to put that up there. Okay, now problem number 4 says, true or false, all isosceles trapezoids are similar. So we just need to consider all our possibilities here, you know. Isosceles trapezoids, as you may very well know, have to have 2 matching legs. So that's an isosceles trapezoid. You know, this is an isosceles trapezoid. And to be similar, of course, that means basically they have to have the same shape. Just one is a blown up or shrunken down version of the other. I hope you can tell from just the pictures alone that I made here that these are not similar. Could they be though? Sure. You know, if I were just to blow one of these up and have a bigger version, you know, that would work. You know, that would be similar. But they don't have to be. You can see this one. This one's got short legs and is kind of widened out, where this one has tall legs and is kind of skinny. You know, so the shapes don't even match in the first place. The problems that I'll probably give you on the test that deal with this type of true or false situation will more than likely deal with triangles instead. So don't forget the techniques that we have in this chapter as well that you can even use to make sure that triangles are similar. And that would be, you know, those techniques AA, SSS, and SAS. You know, some of those may, you might be able to justify whether triangles would be similar using, you know, one or more of those techniques on the problems that I might put on the test. Okay, so there's the first 4 problems. Let's take a look now at number 5 there on your review sheet. Okay, on these next couple of problems, 5 and 6, they want us to determine if the triangles are similar. And again, don't forget what I just mentioned a little bit ago. These are ways that we can justify whether triangles are similar. And they even say on 5 and 6, they want you to give a reason if they are similar. Okay, so on number 5, they've got a picture that looks, something like this, where they give you 23.8 for that length, 3.6 for this one, 1.2 for that one, 6.8 for this one. They tell you this is a 42-degree angle, and this down here is also a 42-degree angle. Okay, so when you look at a problem like this one, and you look at our 3 options that we have over here for proving triangles similar, I hope it's obvious. We have 2 sides and the angle in between. 2 sides and the angle in between. So 2 sides and the angle in between means that we should be able to use SAS to do this. But don't assume that it already checks. You still have to make sure that the sides are proportional. Okay, on any of these techniques that use sides, the sides have to be proportional. Okay, so make sure you check that. So down here, I'm just going to put 23.8, which corresponds with, I hope you see, the 6.8 over here. I'm going to put them in a ratio, putting the bigger one here over the smaller, and then I'm going to do the same here. Big over small, 3.6 over 1.2. Okay, and you can either reduce these fractions, or it might be just easiest to divide it out as a decimal. You know, just let your calculator do all the work for you here. So 23.8 divided by 6.8. This goes into here 3.5 times. Okay, so I'm hoping to get the same thing here. So if you take 3.6, divide it by 1.2, that comes out to 3. Yeah, I hope you see that's not a match. Okay, 3.5 and 3, that's not a match. Okay, so even though at first glance you might have thought, oh yeah, by SAS they should be similar, the sides didn't check, so on this one we have to say no, they are not similar. You might say it failed that test over there for the SAS. Okay, problem number 6, same situation. I want to know if the triangles are similar, and if so, you have to give a reason why. Okay, on this one, they've got a triangle like this, and another one like this, and let's see, they give you 125 degrees for that angle, 22 degrees for that one. Up here, this is 33 degrees. This one, 22 degrees. Okay, so they only gave me a couple of angles on each of these. No sides involved. So AA is the likely method that we'd have to use to show these triangles similar. And at first glance, you might think, oh, it's another no. Because even though the 22 matches the 22, the 33 does not match the 125. But don't forget, there's another angle yet in the triangle here yet. So if I were to find this last angle here, for example, I could find that by taking away from 180, which I know all three angles add up to. We could take away the 125 and take away the 22. Okay, so if we do our math here, 180 minus 125 and minus 22 gets me down to 33 degrees. Turns out that last angle does in fact match this one right there. 33, 33. And if two of the angles match like we have here, that's enough to say the triangles are similar by AA. So yes, by AA. Okay, don't forget to be able to give us a reason on these problems if it is a yes. Okay. Let me erase that. So we can move on to number 7 on your review sheet. Okay, on number 7, they've got a picture of all these different lines that run parallel to each other. So these are all three parallel there. Okay, and then there's some transversals running along here, like one here and another one along here. And they give you some measurements. They tell you that this segment here is 9. This segment here from there to there is 12. And finally down here, this segment between here is 8. And they want you to be able to find this last piece down here, this segment between those lines. Alright, so if you remember correctly in this chapter, we had a theorem that stated that if you have a bunch of lines parallel like this, in fact we had a theorem that just said if you had a triangle and if you run any segment through the triangle parallel to one of the sides, then it cuts the other sides into proportional parts. So all these parts are going to be proportional to one another. So I should be able to set up a proportion to get my answer here. So as long as you're consistent in your pattern here, it's hard to go wrong. You know, you could put 9 over the x. So I'm going top over bottom, and I could do it again here, 12 over 8. Or you could go 9 over 12. You know, went left to right, and then x over 8. You know, either of these would work because, I mean, after all, the first step you're going to do is cross multiply. You're going to take 12 times x. Oh, look, 12 times x. And then you're going to take 9 times 8, which is 72. Oh, look, 9 times 8. Okay, so either of these would come up with the same solution. I'm going to finish this one off then by dividing by 12. So if you take 72 and you divide it by 12, that should give you 6 for that length right there. Okay, on this problem, I believe it's labeled as DE. Okay, so that was problem number 7. And we're going to erase that one now so I can show you now problem number 8. And problem number 8. On this one, we've got a picture that looks like this, and they show a midpoint right there and a midpoint right here that are being joined. Okay, and then they tell you, well, this length along here is 3x minus 1. This length along there is x plus 2. Now, anytime you join the midpoint of one side to the midpoint of another like this, not only are those parallel, but we had a theorem in this chapter that mentioned that the length of this one compared to the length of this one, well, this one will only be half the length. You can see it's smaller, okay, but it'll be exactly half. So if this one's exactly half of that one, then if I want to be able to write in equation, if I want to be able to make them be equal, then I'm going to take the smaller one right here and I'm just going to double it. 2 of those, 2 of these should equal 1 of those. So there's my equation. Okay, now I just got to solve for x. First thing I'll have to do though is distribute right here. So 2 times x is 2x, and 2 times 2 is 4. And at this point, I've got a Sheriff Bandit situation. I'm going to get rid of the weaker one. Okay, so now I'm down to x minus 1 equals 4. Add 1 to get that x by itself. And we find that x is 5. Problem number 9. On problem number 9, we've got a picture of a triangle, and there's a segment running through the triangle up here that runs parallel to this one down here. They mention that this is 4, this is x, this is 6, and the whole length of that side is 21. Okay, now in the same section that this was in, there was a theorem down here that said when you run a line parallel like that to this side down here, it cuts the other 2 sides into parts, and those parts are proportional. So I'm going to do a little bit of math here. We're going to find this length first. If the whole thing's 21, if I take 6 off of that, then that's going to leave me with only 15 then for this part down here. And the reason I wanted that part down there is so now I can set up a proportion by looking at the different parts over here. And, you know, as long as you do a consistent pattern again, it should be a good proportion. So you go top over bottom, or left over right. It'll give you the same result. You know, the cross products will still be the same. All right, I cross multiply, I get 6x and 4 times 15. So that's 60. Divide by the 6, and you have your x. X equals 10. So there you have problems 8 and 9. Okay, now on the next page of your review sheet, you'll see problem number 10. Problem number 10 is a fractal. Okay, and they have an iteration process already typed out on there for the fractal. And they mention on number 10 that they want you to use the square already provided there to be able to draw a stage 2 of the fractal. Stage 2. So if it's a stage 2, that means you should go through the iteration process not once but twice. Okay, and that doesn't include the original original square already provided for you here. You know, this does not count right here. That's not stage 1 already. Okay, I got to go through the steps first to complete stage 1. So the first step said find the midpoint of each side. So let's say those are my midpoints of each of the sides. Step 2, connect the midpoints of the opposite sides. So this midpoint, I'm going to connect to its opposite side down here. And this midpoint, I'm going to connect over here to this opposite side. Step 3, shade in the upper left and lower right squares. Okay, shade in the upper left and lower right squares. Okay, and then it also mentions repeat only in the unshaded squares. Okay, so I've gone through the iteration process once now. So this is stage 1. Now they wanted us to draw stage 2 though, so I'm not done yet. Now I have to go through the iteration process again, and remember it said to only repeat it in the unshaded squares. Okay, so once again I'm going to find all the midpoints. Midpoint, 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 midpoint. Midpoint, 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 midpoint. Said connect the opposite sides, the midpoints of the opposite sides. So connect there, connect there, connect there, connect there. And then it said, remember, shade only the upper left and lower right squares. Upper left and lower right squares. This now would be stage 2, because I've gone through the steps twice. And that's what they wanted us to draw, so I would stop right there. If you keep going on a test like this and they said draw stage 2, I'm going to count it wrong. If you didn't go far enough, I'll count it wrong. You need to know exactly where to stop. Okay? So whatever the stage is, that just tells you exactly how many times you go through the iteration process. So stage 2 meant we went through the process twice. Okay, now there's 2 more problems on this review sheet, but both of them are on graphs that I need to set up over here. So I'm going to end this video. I'm going to create a second video then that'll show you those last 2 problems.